Yeah, happy to be here. What I will talk about is not so much on the vision end of things, although, of course, we see a lot of promise for neuromorphic computing, spike-based computing in particular, for vision. But really what I'm going to talk about is just first proving the value of spike-based neuromorphic computing, since if you know anything about the space, it's a bit of a controversial topic. What are spikes good for? Why would we even build a chip that is, confusing the trees from the forest kind of thing? The planes don't flap their wings. These kind of arguments you've heard a lot, and I'm sure. And I will try to provide evidence, which is what we've had very little of in this field, to say that, in fact, we do see computational value in this direction, and it's quantified and pretty indisputable. So first, to set the stage, here is just the landscape of computing from the lens of Intel, whom I represent, of course. We're in the business of building chips, for the most part, that solve real-world problems. And we want those chips to be general and solve a large class of problems very efficiently. And today, of course, we're finding a need to broaden the architectural portfolio and find new architectures that can enable highly efficient computing like we might find in the brain, or intelligent workloads, and in general things that the von Neumann model just doesn't support very well. So the question is, where can we look for inspiration for that? And obviously, machine learning would be a natural place to go. And machine learning, which I've illustrated kind of on the left here, is a disciplined, highly rigorous mathematical approach for algorithm discovery. And the great thing about it is that it works really well. And you know precisely the parameters and the properties of those algorithms you derive. You know what to apply them to. You know the convergence, all kinds of good properties. The downside is that you can come up with anything through that approach to algorithm discovery. So in a way, it sort of presupposes a highly general underlying computing architecture, which is really an implicit assumption that algorithms researchers throughout the world have in their brain. I mean, that's been the success story of the von Neumann model, and now today's more modern matrix arithmetic accelerated forms of that, which lead us into a space which is giving great value today, but is not necessarily constrained in the way for efficiency and achieving the desired objectives of the real-world intelligent devices we might want to build. And so for that's what leads us to look at the neural direction. So neuroscience, brain-inspired approach, where we see the existence proof, of course, which still today is the only truly intelligent device, the brains of all kind of shapes and sizes in nature, and to try to understand the principles of where does this amazing capability and this amazing efficiency come from, and try to abstract that and apply it into the design regime that we operate in. So silicon, CMOS, chips we can build today. And so that's the focus of my research program at Intel and Intel Labs. So it's this intersection broadly between the green region and the orange region. And what we found is that the spiking neural network model is really the simplest enhancement you can make to the ANN model that greatly broadens the algorithmic space of what neural networks are capable of computing. And so for that reason, as well as various other perspectives on how they provide sparsity in time, therefore efficiency, number of properties, we're investigating silicon research chips in this domain. One point about this kind of middle region, circle the one there, there's a lot of confusion for those who don't know much about the neuromorphic space, sort of an assumption that what we're doing is trying to build better deep learning accelerator chips or something like that. And that's really not the primary point of our research. It's an understandable point of confusion because the spiking neural network model is in many ways a generalization of what an ANN does. Therefore, you can generally map standard neural networks into a spiking algorithm, but that's not necessarily the best place to how to use spiking neural networks. And there's a variety of other properties. It's not all about the spikes by any means. There's many different architectural principles that are related here. You can see from all these example algorithms, we're looking at largely learning. So putting learning into the silicon and enabling learning at a much more efficient way, whether more data efficient or more power efficient. These are the types of things we see happening in the brain, and we see ways to implement that with this architecture. But then there's all kinds of other algorithms too, and we have early results in many of these categories. Things like doing probabilistic inference and SLAM, of course, which is of interest to this group. Constraint satisfaction, solving shortest paths in graphs, and all kinds of things that you don't normally necessarily associate with neural networks. So with that as an intro, this is the chip we built. You may have heard of it. It's called Loihi, named after an underwater volcano off the coast of Hawaii that's going to emerge any day now in geologic time frames, hopefully earlier than that in our time frame. And you can see just from the chip plot here that it's a very homogeneous architecture. It's literally an arrayed tile of a multiplex digital neuromorphic core. And I'll show you a little schematic in a minute. Each one of the cores implements up to 1024 neurons, and they all communicate through these spike messages. So it's event-based processing pushed all the way down to the transistors. In fact, the chip is almost entirely implemented with asynchronous design technology, which is actually my team's background. For 20 years, we've been building commercial chips with this technology. And that allows for various advantages, but mostly what we focused on here is a feature set of trying to get the architecture right for a spiking neural network chip. For example, integrating learning behavior, learning rules that are distributed through this mesh of neuromorphic cores so that the learning can be completely efficient and you're not moving data constantly through the chip. Also note that there's no off-chip memory. This is all fully contained, meaning we don't have DRAM sitting next door. It's a spatial architecture. There's computing and memory all fully intertwined at the internal scale here. We've implemented it, aside from the asynchronous design methodology, it's actually a totally standard manufacturing process. So I describe this as maybe about 80 to 90% of the way towards a commercially manufacturable chip. Really, it's just scan tests that we lack, which would prohibit this from going into high volume manufacturing. But it's otherwise fabbed in standard 14 nanometer FinFET technology, just like we produce all our Xeons and Core chips in your laptops. So it's absolutely commercializable technology, though we have no plans whatsoever to commercialize Loihi itself. So this is just a very boring chip plot, chip diagram, schematic view of the chip. You can see that it's this arrayed neuromorphic core. On each periphery side, planar direction, we have an off-chip interface, actually. So we built scalability into it, so we can hierarchically extend the mesh, this neuromorphic mesh for the spike signaling, so that we can effectively, logically put together as many as 16,000 chips if we wanted to. We won't build a system that big, but that's the theoretical scalability. We do have these three little blocks marked LMT, which are actually x86 von Neumann CPUs. They're x86 processors. So we found that this is very essential. Even despite the power you may get out of a neuromorphic architecture, there's always a need for housekeeping, data encoding, decoding. The world obviously does not speak spikes, so at minimum you have to convert into this spike domain and back, and you want to put that compute as close to the neuromorphic mesh as possible for efficiency. So that's there for a number of reasons. You can do all kinds of other things with it. You can get crazy with neurogenesis algorithms, structural plasticity, just writing code now that if you have an algorithm that happens at a slower time scale, you're free to go and modify and interact with the neuromorphic neurons however you wish. So these are the systems we built so far, or are building in the last case. Generally speaking, we're trying to span the whole range of scalability. So right now, our workhorse is this kind of Nahuku, as we call it, which is a board that has 16 chips on the top, 16 chips on the bottom, so 32 chips, about 4 million neurons. And we have made those available for a growing network of researchers to log in, use Slurm job scheduling, and it's a very straightforward process. Just get up and running and start running algorithms. For more deployed, embodied kind of applications, we have this Kapoho Bay USB stick, which you can plug into your laptop and and connect up a DVS camera, for example. We have the AER interface to the Davies camera supported there, and as well as any other sensors, actuators, those kind of things. That's what that Kapoa Bay Edge device is intended for. And then we're building this kind of more scaled up, rack-mounted 5U chassis that will have up to 768 chips in it, and that is actually at a pretty advanced stage of development, not quite working yet, though. We've spent a lot of time on software, so of course this is a completely different architecture. It needs to be rethought out from the bottom up. What we really have in a Loihi system is a highly heterogeneous computing architecture, where we have the neuromorphic cores, which is the workhorse, but you also have CPUs at a variety of scales away from that mesh. And so it's really a complicated runtime that has to be running on top of that, with a compilation step that allows you to take neural network descriptions as well as supporting processes, which eventually will run in von Neumann architectures, and then place and routing all of that and scheduling it into the underlying hardware support. And of course, that also means orchestrating interaction with sensors and DVS cameras and that kind of thing. But this is all working today. Obviously, it's getting better all the time. We're focusing a lot now, too, on integrating with third-party frameworks. So Nengo is probably the best example of that. That's working very nicely right now, but we have others planned. Now, to make progress and advance this field of spiking neural networks, neuromorphic computing, we have this community, the Intel Neuromorphic Research Community, that we've launched over a year ago now, and we're supporting a number of workshops, events like this one, although we don't have a demo here, unfortunately. But so building a network of people that get access to the system and can help solve the real hard unsolved problems, which is the algorithms and the applications. So this is open to anybody, whether you're corporate, academic, government. We have over 60 groups now, 50 active projects engaged. So if you're interested, email inrc_interest@intel.com. I'll flash that up at the end. But that's how you can get involved and see what address your curiosity. Okay, so moving on to the results and the algorithm. So really this is the hard part. I mean, this is the stumbling point. When you recognize that, well, this is not just a simple matter of taking deep networks as are working beautifully today and just translating them and running on this. It's really about discovering completely new algorithms. This, of course, is a very, very hard challenge. So the way we can think about this and break it down back, zoom into that Venn diagram I showed earlier, and there's what I call the low-hanging fruit. So there is the deep learning derived approaches, and this is really what is most accessible and is working quite nicely actually right now. And even within there's a variety of different techniques that can be approached. So one is just the straight conversion approach. You take a DNN and then you just train it as if it was an ANN, as you normally would, and then you just convert it. Just represent the activity of these neurons with a spike train, where the number of spikes is corresponding to the activation value that you would otherwise represent as a graded single, real number. And so that's not at all the sweet spot for neural networks. There's so much better things you can do, but it is certainly a starting point, and it's relatively easy to get that working, and actually can give surprisingly good results that I'll show. The next step beyond that is to actually apply backpropagation to spiking networks. So now you approximate this highly discontinuous, non-differentiable activation function of a spiking neuron. You approximate that as a smooth function that you can actually apply backpropagation to. And that is just beginning now, just in the last year and a half, starting to actually yield some good results. And in fact, Garrick, coming right next, will talk about some of the results on Loihi with that technique. And then beyond that, we can start thinking about how can we take the backpropagation algorithm itself and approximate it using the constraints of neuromorphic hardware, which are also the same constraints as in the brain, meaning local learning rules, that you only update weights based on locally available activity information, perhaps with some neuromodulatory sort of error signaling that are projected in as well. But basically just with local learning rules, not achieving the same level of accuracy as you might with a traditional backprop running on a GPU, but at least can give you some level of fine-tuning, let's say, deployed after you've perhaps pre-trained a network with the full backpropagation algorithm. So that's just starting to make some progress, and hopefully we'll have some results coming up, but nothing quite yet. Now, on the flip side, we have the neuroscience inspiration. And there's a number of interesting algorithms from this domain which actually do work. And the problem is that they're not generalized, right? There's no mathematical theory that sits under them, so that they're more examples that are kind of interesting to look at and think about, but are not ready to be deployed and solve real-world problems in a general way. But it's very important. This aspect of just harvesting neuroscience intuition is a very essential part of this whole research problem, I feel. And what that ultimately allows us to do is put some mathematical theory underneath those examples. Use them as experimental evidence that there's some value in this direction. Okay, let's try and apply some math and really figure out what are the mathematical principles. And at that point, then they can be generalized, they can be applied to a lot of other problems. So the dynamic neural fields Julia presented earlier, there is some good math behind that. And then the next problem is how to construct these and create large-scale networks that right now only Julia knows, but hopefully more in the future will. But yeah, in this mathematically formalized domain, there's actually a growing list of examples here too. So I'll show some of them, but it's pretty exciting that this is actually a pretty fast-moving domain. There's a lot of new results that are coming. Okay, so the lowest hanging fruit of the lowest hanging fruit. The simplest possible thing is taking a deep network and just training it as if it was a standard ANN, and then converting it into spiking form. And so a collaborator of ours, Applied Brain Research, this is Chris Elias Smith's company, if you know them, did this for an audio keyword spotting network. So the kind of Hey Siri kind of problem, right, of just picking out a keyword after MFCC filtering. And this actually works surprisingly well. So the MFCC filtering in this case does a spatial projection of the audio signal so that you don't really need to do much rate coding of these post-filtered values. It's already pretty spatially mapped. And when you map that into Loihi then, we find that Loihi has the best energy per inference of any commercially available architecture that they tested. And they tested a wide variety of mobile GPU, full-blown big GPU, CPUs, and the Movidius neural compute stick, an Intel product. You see that it's 5 times lower energy than the neural compute stick, which is exactly this kind of a domain of inferences is what that's intended for. Now, there's a couple caveats here. So first of all, this is the batch size 1 case. So there's no batching of the data samples. This is you receive a sample from the sensor, you perform the inference, and you move on. This is what you want if you're in a real-time environment where you're not wanting to wait and incur the latency of batching up many samples. Secondly, the efficiency, the accuracy is slightly lower, and that's, I think, a consequence of this translation methodology. This wasn't actually trained really for spikes. Now, interesting results, though, here is when you start looking at the scalability. So this is one of the major promises of neuromorphic architecture. It's highly parallel, fine-grained, granular computation, and the temporal sparsity means that communication doesn't become the same bottleneck as it does, certainly in a von Neumann architecture, but even in any architecture where you don't get the benefit of any temporal sparsity. And so you see that in the data here. As you scale out, so the 2 other charts are showing the inference speed and the energy per inference. And the orange bar is Loihi. As you go up to about 10 times the size of the network, actually, 10 times the size of the original network, the performance per inference is flat in the Loihi case. And for Movidius, it's dropping, 1 over it's Amdahl's law here. There's the memory bottleneck is what you're seeing. And of course, the energy is low, and it stays, much lower. It has a smaller incline here. So we're 10 times lower energy for the larger network. So anyway, that's the simplest possible example, and we already see some computational value. Now, jumping to the other extreme, we have this more bio-inspired algorithm, although, in fact, in this case, it's fully mathematically derived from this lasso loss function. If you're familiar with lasso, this is a sparse coding problem where you want to reconstruct some input or explain some input with an overcomplete dictionary of features. Of course, it has application in the image processing domain. You guys are all probably well familiar with this. So you can mathematically link this to both a rate neuron implementation and a spiking neuron implementation. The best conventional solvers solve this with gradient descent, ISTA. They make some optimization. It's called FISTA. In our case, we just go through a different mathematical process, building on the ISTA formulation to put it into the spike domain. So we can solve the same exact problem, the same loss function there, to the same objective value, although albeit at lower, we can get a less accurate solution, whereas you can take a CPU solution, of course, and run it for much longer and get to a much more accurate solution. But if you evaluate the performance and the energy efficiency compared to FISTA, we have very large gains. And once again, we see a very compelling story as you go to larger and larger problems. So here, the parallelism in the architecture just keeps giving better and better results, up to orders of magnitudes. So 10,000 times faster, for example, for large convolutional lasso problems. Now, this is probably unfair for the CPU, this regime, ultimately, because it's just completely thrashing the cache. So it's just doing tremendous amount of thrashing in that memory, which could be optimized. Okay, so then we also have a spiking version of the LSTM network, so what's called LSTMs, or LSNNs. This is coming out of Wolfgang Maas's group at TU Graz. It's exciting because for the first time, spiking neural networks can start to achieve the accuracy of an LSTM, of problems that previously you can only solve with LSTMs. We've benchmarked that now for small problems, and this is, by the way, using now the native backpropagation applied to spiking neural networks. And this is a big eye chart. I think the bottom line is that Loihi gives superior energy and performance, inference, and even throughput in the batch size 1 regime. And if you batch, you can see the biggest GPU here, the highest end GPU, can certainly beat on throughput, ultimately, inference throughput, but still does not pass Loihi in the energy efficiency. So, and then just for variety, I have a graph search example. So this is solving the shortest path in a graph. This is Dijkstra's algorithm. Everybody learns this in first CS class. And you can solve this with propagating wavefronts of spikes. So single spikes that are propagating through the graph, and it's recording the critical path by nature of which is the shortest in time that it took to find the destination. And then you can traverse backwards through that graph and then find what the shortest path was. And here we've gone and benchmarked this again, scaling up to big problems, big graphs. So these are small world networks with 100,000 to 1 million nodes in them, 100-dimensional. So each node has 100 other connections, randomly rewired a little bit to create the small world. And we find that Loihi can find the shortest path up to 100 times faster than a Xeon for these same problems, applying Dijkstra. And the Xeon has a big spread because there's various uncertainty in how for a particular problem, how long it will take. In Loihi's case, it's just basically always the critical path in the graph. And there's, again, a nice scaling argument. So it's scaling in a sublinear way in the total number of nodes. And let's see, the last algorithm I'll give is solving constraint satisfaction problems. So this is stochastic neural network. So you add noise into a spiking neural network, and you can form, if you configure this in the right way, the network becomes a stochastic dynamical system, and it converges to a certain distribution of macro states in this network, which you can sample from and perform various probabilistic computation. And so in a certain formulation, you can solve constraint satisfaction with this, and there's been various other examples. In fact, the same student at Manchester who did this for the Spinnaker platform came and ran this on Loihi, and was really overjoyed that we were getting about this 4 millisecond time frame to solve these problems, like coloring the world map and Sudoku. This is about 100 to 1,000 times faster than even what Spinnaker can do for those same problems. So this is kind of tying into what I mean by realizing the promise of spiking neural networks. We haven't yet had chips that really deliver at the performance level that's possible for this architecture, and I think we are now finding that this is possible. So as a summary of some of the quantitative results where we have both performance and energy for, this kind of complicated plot is sort of what the measurements we have so far. On the x-axis is the energy to solution as a ratio of the the conventional solution on a variety of different architectures, algorithms, to Loihi's energy to solution. The y-axis is the time to solution as a ratio of the conventional to Loihi. So upper right is better for Loihi, and then bottom left is bad, and this diagonal line corresponds to the kind of the parity energy delay product. And you can see that we have the converted blue dots. These are the DNNs converted to the spiking form. These are providing gains, but not the best gains. The LSNN model, where we now have some recurrence and there's some lateral feedback and there's some benefit from driving the system to equilibrium, we get even better advantages. And then we have this lasso example where we see, where we see the big gains. And here we see, of course, the improvement as you go to larger problems. You see the dots shift out, and then you see the effect of batching. This gets a little complicated, but as you batch, you can get to better energy efficiency on the conventional architectures. But if what you're interested in is your time, the latency to your solution, you're really not getting any benefit by batching. In fact, it's worsening it a little bit. Of course, the throughput comes up. So if what you're interested in is throughput, well, then batching, of course, is a good way. But ultimately, that's I hope, presents some compelling evidence that there's value in this line of research. We're making some progress, and it's exciting, to see where this may go. So there's a lot of work still to be done. Some obviously in the event-based sensing domain is one compelling area, but there's a variety of other application spaces that we're also interested in to try to harness the benefits that this architecture provides while trying to offset the high cost, meaning the limited scale of problem we can solve in a single chip. So to solve the same problem, it requires higher costs because we don't have the DRAM. But ultimately, there's that it's finding the right niche for this technology is where we're at. So I'll end there. I'm running over time.